Hey everyone, I am Sam Charrington, founder of TWiML, and today we are going to dig into Qualcomm AI Research's AIMET Toolkit. AIMET stands for AI Model Efficiency Toolkit, and it's something we've talked about on the podcast a number of times with folks from Qualcomm AI Research. And I'm excited to have Abhijit Khobare, Director of Software Engineering at Qualcomm, here to walk us through the toolkit and explain how it's used. Abhi, welcome.
Hi, Sam. Happy to be here.
Absolutely. Let's jump right in and start out by having you kind of refresh us on what is AIMET.
So AIMET, or AI Model Efficiency Toolkit, is this product from Qualcomm Innovation Center. And the Qualcomm AI Research folks have been working on this. And it's a tool to help with model quantization and model compression. So AI models, take AI models, make them more easy to deploy on edge devices, right? And it does all these techniques. There are multiple techniques in there, and we'll cover those in detail later. But that's a like a overall thing of what AIMET does. So there are, I think from the GitHub, I would just like to point out that, there are several releases. We keep making releases maybe every couple months or so, adding new features. So please check those out. There is documentation, installation instructions. You can ask us questions either by creating an issue, or, if you want to point out something, or going to the forums and asking questions over there. And we are always interested in having people contribute to us and help us out. So I would really welcome that as well.
So Abhi, before we jump into the tool itself, take a few seconds to talk about why quantization matters and what some of the benefits you're seeing in applying quantization techniques generally in the toolkit.
Excellent. There's a good segue into what I was going to start with. So AI has been there in the mainstream usage for several years, maybe a little more than 10 years. And, it started with a lot of deployments on the cloud. Like you have the cloud, AI cloud keeps growing every year like crazy. But what you've seen in the recent, few years is there have been edge devices, right? And edge devices, things you hold, you touch, they are running AI. And it doesn't, it's not one versus the other. I think in a world, there's going to be both, AI running on the clouds, AI running on the edge, and they're going to work synergistically. So there are challenges of the AI workloads. They are compute intensive. They are, they also have these kind of, sometimes the tasks may need real time running. So you have complex, but you want to run fast, or you may want to run it with very low power, like you have always on, like you want to say, hello, Google, and have the phone wake up, for example. So, there's all these kinds of conflicting, if you may, challenges here. And if you pair that with the constraints that a edge device offers, so you have, limited, compute capability or memory constraints, there, as opposed to a cloud kind of, device. Yeah. But you also want those things to be long lasting, last, day, like with a phone or something like that, and be very thermally efficient, like have slim form factors and so on, right? So there are all these things come into play. And that's where quantization helps. Because the reason quantization helps is you can, take these models that have been trained on, the big clusters of machines in the cloud, and you can make them ready for deployment on these constrained mobile devices. And so while during training, you may need the full precision floating point 32, setups for training, but at inference, it turns out that you don't need that high precision. You can actually run things in 8-bit integers, and get pretty good accuracy. I actually will show that you can get almost the same accuracy as your floating point 32.
And is reduction in power consumption, is that the only benefit of quantization?
Yeah, so this, this is a big gain you get by, instead of running floating point 32, you run integer 8 bits. You can get like up to 16 times, performance per watt kind of savings, which is humongous. But in addition to that, there are other aspects that are good. For example, floating point hardware generally takes more space than integer hardware. So you could fit in in a smaller space, or you could fit in more capable integer inference hardware in the same space, right? So
and when you say space, are you talking about kind of die and silicon? Or are you talking about servers in a room? Or
I'm talking about die and silicon, but I think
I guess not servers on a room if we're talking about drones and cars.
That is true. That is true. But it does, in a way, it does, how much area in the car gets dedicated to this AI compute, right? So it's sort of related to that. Yeah.
Okay.
There's other benefits also, like memory bandwidth is much more constrained with 8-bit as opposed to 32-bit floats. And that has benefits not just for AI, but for the other workloads running on these devices as well.
Okay. Awesome. So tell us a little bit about the demo you're going to walk us through.
Okay. So today, what we are going to do is we are going to show how we can take a model. In this case, we are going to take a HRNet semantic segmentation model, and we're going to take it and quantize it and see what is the quantized accuracy if you did it naively versus if you used AutoQuant, what kind of accuracy you can get. And we will see real world benefits of what that accuracy means. Yeah, and I want to maybe start off by saying that here's the HRNet model, high resolution network. I think it has, I'm not an expert in the architecture of this model, but it's a backbone that is used for several tasks: semantic segmentation, pose estimation, and so on. And we have selected, I think from the HRNet, which is open source available, we have selected the semantic segmentation model out of that.
Okay.
And it works with several different data sets. But we have specifically selected this data set called Cityscapes. And again, this model was already trained. We just downloaded it. So the Cityscapes data set looks like what you're seeing here. It's a view taken by cars running on roads in Germany, I believe. And so the idea here is to at a fine resolution, segment out different classes in the scene, right? People versus cars versus signs on the roads, or foliage, trees, so on and so forth.
Yeah.
So it's very useful for some an ADAS application, for example.
Autonomous vehicle type of application. Yeah.
And here are some sort of classes that you can see. There are 30 classes here as part of this data set. So let's start by seeing what does it do, right? So I'm not gonna actually run through all the cells here because even an inference takes about 3 minutes or so. But if what this cell has done is we have just loaded the model, and we have just simply done a floating point 32 evaluation of the model. And what we get is a score, a MIOU score. So intersection over union, mean intersection over union score of 81.05. So there's a standard kind of metric used for semantic segmentation kind of use cases.
So that's our baseline here.
That's our baseline, right? So this is what the model was trained for. Somebody spent gazillion time to get to this accuracy. Okay, and now we are trying to make sure that we don't destroy their effort, right? As in our zeal to make it more efficient. And this is what an inference would look like, right? So we took this sort of input image from Cityscapes, and if you take it through this model, you get this semantic map that's overlaid on the scene. And what you can see is like, you can see, hey, there are different classes. We're not pointing out the classes color coded, but you can tell there's a person on a bicycle, trees, foliage, roads, and so on and so forth, right? So it's, and street signs. And so it's like sort of segmenting all of this.
So you brought to our attention that that MIOU score of the 32-bit model. Will we also see the inference time decrease as well here as we quantize the model?
So if the inference time on targets would decrease,
mm-hmm.
So in this particular demo, we are going to show through AIMET. AIMET allows you to simulate the inference off target, but get you the same score as what you would get on target. So it's simulating quantization. So yeah, but your point is right. Like on targets, inference would be faster.
Mm-hmm. And by on target, you mean on the target device? On
target device, like a cell phone or a headset, like AR VR headset, or whatever the target device is.
Mm-hmm. I see you have pain points here. We've been kind of talking about quantization for a while now as deep learning has gotten popularized. And, on the one hand, I hear about how painful it is. On the other hand, you have various vendors kind of suggesting that it's more built into the infrastructure itself and the user shouldn't have to think about it. Like, what is it like in the real world to quantize a model?
So yeah, that's a good, excellent question here, right? So what we have, learned, or at least I have seen, seeing users of AIMET and, using it in real world. So what people care about is, I have a model and I may have several models and I want to take it to this, target device. And I want to, ideally take the least amount of time, least amount of effort. That would be perfect for me, right? Mm-hmm. So often it happens like there are, all kinds of techniques available, but they, most people feel like, okay, it takes too long to run this, or there are several techniques. Which one do I choose, or should I apply more than one, and which order, right? So like it's kind of hard for them to like pick and choose the techniques to apply. And also there's a lot of user touch points, right? So it's like you try one, then see what happens, then you try the other one, then see what happens, or go back to the first one. And so it's like the flow has a lot of like user touch points. Whereas what would be ideal would be to say, you take care of the work. Like, why don't you automate this whole thing, right? Mm-hmm. And just give me what I need. So I think that's a segue into like what the demo we are going to see today, AutoQuant, as it stands, automatic quantization. So it's going to apply things in an automatic fashion, right? It's trying to, the too long part is like subjective. So AutoQuant may take, in this particular case for this HRNet model, it took like about 4 hours to run, which may seem like a long time, but if you think about it, like an alternative to that would be, running several different techniques by hand and with, pauses in the middle, or like running quantization-aware training, which may take several days to run. And so like, some, push button, press the button and wait for 4 hours, or like do it in the night and have it run overnight is, in comparison, a much bigger advantage.
Mm-hmm. Mm-hmm. And now, am I correct in my understanding that AutoQuant is relatively new? Previously, AIMET was more of a toolkit for hand quantization?
So that's a good question. And I think the intent is not to, not to choose. So there are AIMET has a bunch of techniques. They have, we have what we call post-training techniques and quantization-aware training techniques. So post-training techniques, as post-training meaning like no training required, use a little bit of data, and there are these techniques that help. And quantization-aware training, as the name suggests, is training, like it requires fine-tuning and so on and so forth, right? So there are these techniques. I think it's not.
Meaning post-training, you've got a model and, maybe it's a black box from the perspective of training, and what can you do with this model to make it better fit on a target device? Quantization aware training is you've got the data and you want to build the model. How can you take into account quantization while you're doing the training and produce a better result as the output?
Yeah, if we back up, like I think quantization aware training is you still have a trained model. So
Okay.
your starting point is the same, but you now like want to take this model and apply further training to make
Okay.
it like better for the target device.
Got it.
Okay. So yeah, what AutoQuant tries to do is like there are these techniques which are automated in their own way and individually, but it sort of puts like a box around this whole set of post-training techniques, and there'll be more post-training techniques in the future, and it sort of like puts an automatic box around it.
Okay.
Right. So so yeah, with quantization aware training, it's a more general purpose technique and applies to a lot of things, and can, in general, like I think give pretty good results across almost all models. But I think what it does is you need training, like some 15-20 epochs of additional training on top of what was already done. You need hyperparameter tuning, it's training. So you have to, just running 20 epochs is not going to give you the answer. You have to repeat that several times to get the best answer. And you need training pipelines, training data, you need all that set up. And right. So as opposed to it, post-training doesn't need training, right? So that it's more automatic, more push button, and needs just smaller set of samples.
Mm-hmm.
So what we're going to show is like how AutoQuant like would take the post-training quantization and make it automatic.
Okay.
The other thing I would also say is like AutoQuant doesn't preclude quantization aware training. So you could actually, what we see is if you apply the post-training quantization techniques, and then if you are not satisfied with that, where the accuracy is, which happens for like, let's say maybe 10% of the models, right? If you had 100 models, most models, like maybe 80% of the models or 90% of the models could be okay with post-training quantization. It all depends on what your threshold is on what is acceptable, right?
Mm-hmm.
But then for the really use cases where it's critical to get that additional accuracy is where you apply quantization aware training, and you can do that on top of what AutoQuant gives you.
Okay.
Okay, so let me go ahead with this flow, right? So what we would do with AIMET is we go through a process called model preparation. So this is a step towards simulating the model, how it would run on a target device. We are trying to simulate the quantization. So the first step is preparation, and what preparation does, and it's a single line call here, for example, but what you see, and I'm sort of printing something before and after. So what I'm printing before is I'm taking all the modules in the model, and I'm trying to see, this piece of code here is trying to, sorry, I can't select it, but this piece of code is saying it's a leaf module, like it's a layer which is, at the bottom layer, right? There's no other further sub layers to it. And I'm just printing the type of the model and actually putting it into a set. So we see that there are these 3 layers in the model, right? There's actually 1,000 or so layers, but they are all of these 3 types, right? Convolution, ReLU, and batch norm. Mm-hmm. But in reality, there are actually more layers. So there are things like element-wise add or element-wise concat or interpolate. And these may, appear like a plus sign in the PyTorch code, for example, but they actually matter when you run it on a target device. Even that element-wise operation can introduce a quantization noise. And so if we do this preparation step, which is done sort of automatically by AIMET, you will emulate or simulate the target device much more closely, and you can trust your off-target results to your on-target results.
Okay.
And so what this is showing is, we are creating a simulation model. And so what a simulation model is actually the PyTorch model that you gave it, but it'll insert some simulation layers into that model at the right appropriate places to simulate the noise. So for example, it would insert simulation nodes for the model weights and simulation nodes for the more like the layer activations, layer weights, layer activations, that kind of stuff.
To simulate quantization noise in particular?
Simulate quantization noise, exactly.
Okay.
Right. And so the first step here is what we're going to do is we're going to say, okay, let's see what can we do naively here, right? So a naive approach would be to set the quantization parameters, like there are scale offsets and there are some sort of configuration or encoding information for each of the simulation points. And you can find those through data, and you can basically look at the range of values that you see at a simulation point, and then that becomes your basis for how to quantize that portion of the model or that tensor specifically. So this is doing like a absolute min max kind of calibration. So this part of the code is just saying, if I have a model, I'm going to pass some data through the model, right? Some samples.
It looks like that code is relatively boilerplate and not particularly model specific.
It's not model specific. It's not AIMET specific either. And here, what we are going to do is we are going to call back that simulation object that we had with the simulation nodes added, and we are going to essentially pass this calibration or pass a handler, a callback to it, which is going to pass data through the model, the simulation model. And so once that data is passed to the model, then it'll analyze the data that is seen and come up with the scale offset information. And now we can go and do an evaluation. So one interesting thing about AIMET is designed to be user-friendly. So this evaluation is the user's evaluation. It's the same evaluation routine we used up here when we did the floating point 32 evaluation, right? So same routine can be used. It just happens to be a simulation model in this case.
Okay.
And so when we run that evaluation, now, if you remember, the score earlier was 81.05, and that score has reduced to 77.9. So a little more than 3% drop, right? Doesn't sound like a lot. So I think in a way it's good. This model is not like, it doesn't break apart with quantization, right? Which is, I think a good percentage of the models. It's a good start. Yeah. It's a good percentage of the models will fall in this range, like where they are not breaking apart, but they are off, right? And what do we mean by off, right? So I think there's some like sort of examples. So what we are doing is on the left-hand side, there are like 4 examples here.
Yeah.
And on the left-hand side is
kind of visualizing what we're missing with that 3%.
Exactly. Yeah. So on the left-hand side is what was, what the model trainer trained it for. This is the sweat and tears went in this part. And this is what has happened when we try to quantize it, right? So you see in this particular scene, we have highlighted through this red box. There is a sign here and a person standing, behind the sign. You can see a little bit of the person, but the sign is completely gone. Like it has failed to segment it. So this, if you are building an ADAS kind of application, missing a sign may be a problem, right? Yeah. Or in this particular case, there is a person standing on the sidewalk, and that is missed segmenting here, and which may be a problem, again, if you were trying to build some safety into your ADAS application, like this person may be about to cross the road for all you know. And so, this is important information that is missed, right? So
maybe playing devil's advocate a little bit, a lot of what's being missed is on the periphery as opposed to kind of central to the the images here.
Yeah.
Are there also downstream effects in the model for that aren't really shown here? Meaning,
Yeah, let me. I exactly. So I'm gonna scroll down just to show you like what the original image looked like, right?
Mhm.
So what it turns out is like if you see the things that are missed in my perspective seems to be things which are like sort of harder to segment even for human eyes, right? They are in dark blending into the background. So what this means is like the model is not broken, right? That's what it means. The model is it's 3% off, it's not broken, and it may seem somewhat peripheral to this scene, but like what would happen in a real ADAS application is you would run several like models in succession. So you may segment first, and then that segmentation results may go into a sort of a path planning kind of aspect. So based on this, you may say, oh, let me see, is it a stop sign, for example, right? And that may go to a path planning. It may start slowing down the vehicle. If you miss it, then that thing is going to miss, right? So there are downstream effects to applications. Yeah.
Okay.
And in the case of like ADAS, they could like literally be fatal. Okay, so one tool I'm gonna introduce here is called QuantAnalyzer. So this is before the AutoQuant. So what, as the name suggests, what it does is it analyzes the quantized performance. It analyzes the quantized model, and so most people have this question like, okay, I understand there's 3% gap. Like, where did it go? Which layers are, where did I lose that, right? And so what it does is it creates a bunch of visualizations. Like, for example, it has this visualization called layer sensitivity. So what you're seeing on the x-axis is all the layers of the model. And it probably doesn't matter to stare at each layer. If you can zoom in if needed to. And on the y-axis is accuracy, right? So what this is showing is like, oh, the start of the model seems to have some layers which are very sensitive. Somewhere in the middle, there are some other sensitive layers. But one thing, it doesn't look catastrophic, which is kind of goes back to this particular model is not like catastrophically breaking. There may be other models where we have seen like sharp drops, right? And that tells you exactly which layers are actually problematic.
I want to kind of sanity check a little intuition here. Like the beginning layers in a network like this, you might assume to be kind of these coarse grain pattern type, capturing coarse grain patterns. Does it then follow that they're going to tend to be most impacted by quantization because they're so coarse?
So that's a good question. I think I don't know. Probably there's no mathematical answer to that. But we have observed, I think empirically, that the start of the model and the end of the model generally tends to be more sensitive to quantization. Right. And I think what you said, I think that may be a good way of like sort of intuition behind why.
Okay.
So other visualizations it gives is also these kinds of, it gives distribution. So here we are like showing a distribution of weights of some layers. You can also look at distributions of activations, and like take this example like here. So what this is showing is there are like outliers which are very, very rare, and there are most of the weight is in the central portion over here. So we could in theory do better on this part by not caring about these very rare outliers and sort of clamping a bit. And this is one of the techniques in AutoQuant which will like find better calibration. So this particular graph is showing like a distribution of tensors in the model, right? So for example, on the x-axis, it's showing like literal ranges, like what are the values inside the tensors and where do they lie? and on the y-axis, it's showing like incidents or like a PDF, right? So this is, think of it as like a PDF,
Okay.
right? And it's showing that, so like a lot of values are centered around the zero, very tightly close to zero.
Mm-hmm.
But there are some outliers which may be at this 0.5. So it's not terribly bad. Sometimes you see these layers which are like, the outliers are like really out there, like 30,
Yeah.
40. But even so, you can do better here. Like you could clamp out some of these outliers. So I think techniques like AutoQuant would do this for you.
Is this also saying that this particular network is particularly sparse?
I don't think it does. It may seem like this, or this particular layer may seem like this. So there is probably some truth to that. But like if you see, for example, other layers, like like take this, for example, like it's showing, maybe the things around, there are like some negative values around zero. There's a lot of them here, as you can tell. Yeah, the zeros are probably also there. So it's also kind of showing some sparsity here.
Okay.
Okay.
But not unusual, like it didn't jump out at you. Like there's a common pattern for these kinds of networks, it sounds like.
It's common pattern, yeah. I don't think that in itself has a bearing to quantization noise.
Okay.
Yeah, by the way, like absolute zero gets represented with no loss. That's one of the things we at least in AIMET we do is like, don't mess with the zero.
Yeah.
Zeros are very important. Okay. So next we are going to apply AutoQuant. And what AutoQuant is going to do is it's going to apply several of these techniques in succession, right? And it's going to check, I applied cross-layer equalization. So the techniques we had seen here, like there are techniques for calibration, there are techniques for cross-layer equalization or adaptive rounding. So it applies all of these techniques in a order, given some sort of intuition on which ones should be applied first, which one should be applied second, when do we stop. And like, just to quickly recap, like cross-layer equalization is like, it tries to equalize weights so that the quantization noise reduces. Adaptive rounding is very interesting. It like learns how to round, like instead of rounding to the nearest value, you actually learn a grid, which tells you how to round each value. And then you sort of apply it on top of on the tensor. So if we go back, like it applies all these techniques, and what you give it is like a drop. You basically tell it, hey, in this case, I'm saying I want to tolerate 0% drop, right? So that 81.05 where we started out, I want to get there, right? So it's going to try its best. And if it doesn't meet it, in which case, in this case, it's not going to meet it, but it'll give you the best model that it can get, right? So the reason I chose 0 here is I wanted to get the best model, like what's the best it can do, right? And so we set it up with some parameters. You give it some data. It needs some representative data to do its job. And you give it some standard add around parameters. We generally don't touch these, and we use it in a standard fashion. And there is a single call to make, AutoQuant.apply. And then you can see that it starts like applying, it starts batch norm folding, it starts applying cross-layer equalization. So it keeps going and starts applying different techniques. Yeah, one of the things we want to work on is to create like a nice a report, maybe even visual, to say what techniques did I apply. Like if I could get something like that at the end, that'll be great. So that's not there today, but we aim to build something like that. But once it's done, it gives you back the resulting model. Like once it's done, it'll give you back a model. It'll give you some other statistics. And what we can take is we can take that model and like create another simulation model and sort of run inference again. And now we see that the score has improved. Like if you remember, like with the naive quantization, our score was 78.9, like, or 77.9,
yeah,
like 3% off. And now we are like 0.3% off, right? Okay. So it has made a dramatic improvement.
Yeah.
And like, what does that mean, right? Like, here's what it means. Like these hard
still
cases
see our
where
sign.
it's the sign, you can see the sign now,
Yeah.
right? Compared to no sign, sign. Or take the next image, person, like person was missing, person segmented, right? Or a cycle missing or a person missing, segmented now, right? Like, sorry, I'm
And
pointing.
the square on the left-hand side, the gray square above,
Yeah.
what's that?
That's this is in the original image. We're just hiding a logo.
Okay.
It's got, yeah, nothing, no bearing to the results. Yeah.
Got it.
Okay, so yeah, just keep, yeah, for every scene it has made a difference.
Okay. Oh, very cool. Again, I think it's clear, but as the engineer, data scientist, you weren't tweaking parameters, you weren't kind of doing anything to guide it to this result. This is just the go do it result.
Yeah, for this particular model, no tweaking needed. We basically ran AutoQuant, as you saw, like a single call, and you gave samples to it, but there's some guidelines on how much samples it needs and so on. These parameters are all like defaults. There's a lot of tweaking you could do, but you don't need to tweak it for the most part, right? That's, I think, the point here. And like, if I were like really interested in getting this model to target, I would be super happy, because 0.3% off is like almost the same as floating point 32 with like that 16x gain in performance per watt, right? So that's absolutely fantastic.
And I may have misunderstood something, but why in the case of the quantized model do you have to take that step where you introduce the quantization noise? Is that what that simulation step was, or am I confusing things there?
Sorry, yeah. So going back, so I think we had a model, like this is the floating point accuracy, and we want to just get a, what would the accuracy look on a target device, right?
Yep.
So you could run it on the target device, but generally more steps to run through. So what we are doing instead of running on the device, we are trying to simulate what would happen.
Yeah.
With the same kind of results off device. And so that's what the simulation is doing. So it's simulating the noise. Yeah.
But then it looks like you did the same thing later with the quantized model.
Because what you would do is, like, now you took this AutoQuant results. So that's a good question, actually. What AutoQuant is doing is it's still resulting in a floating point model, but it's a better model for the target device. So we have optimized the model, but it's still a floating point model. So if I took this to target, or to a target device, I would run through some things and then it runs. So it's trying to simulate, okay, now if I simulate, what is my answer?
Got it.
Yeah, I mean, this is a starting point, if you may. I think we aim to continue improving this AutoQuant, add more techniques to it. For example, like, there are different calibration techniques on how to find how to clamp it properly. And so we aim to add that into the mix and search different calibration techniques, for example. And we plan to add more visualizations to that analyzer so that it can sort of give you some more information. So one of the sort of practical aspects of knowing that information is you could use what we would call mixed precision. So another way to solve this problem, if this is not enough, if 0.3 is not enough and you want to hit more, what you could say is, okay, let's look like these layers here seem a little more sensitive. Like, instead of running it in int 8, why don't I run it in int 16? Right? So an AIMET would allow you to do that in you can specify this layer I want in 16 bits, and it'll let you do that. So that's a practical usage of finding information like this. And then we also have a AIMET model zoo. So again, on the same organization called QUIC, Qualcomm Innovation Center, where AIMET is a project. There's a parallel project called AIMET Model Zoo. And so what we do is like, hey, great set of techniques, but like, what if, why don't you like pre-optimize models, like particularly for backbones and so on, right? So we said, okay, great, we can do that, right? And so there's some like 18 models here currently pre-optimized, and you can see some results on how they have come pretty close to floating point accuracy, and ready to go, TensorFlow and PyTorch. And you can just download these models and off you go. Like you can short circuit your work, right? But then often you will have heads that you attach, or you may have a custom model that doesn't conform to any of the known backbones, and then so you can apply the technique. So you have best of both worlds.
And with the Model Zoo, are those models AutoQuant models, or are they more hand-tuned and more greatly optimized?
So yeah, to be completely like open, like I think there are some of these models have been using AutoQuant, but there are others which before AutoQuant is somewhat recent, and so before that people applied the same techniques that AutoQuant would apply using that intuition. So actually, the way AutoQuant was like envisioned is because hey, there is the smarts that humans are putting into play. Like, why don't we automate that, right? So I think all of that knowledge went into making AutoQuant. So I think our intent would be to like go back and maybe run some of these through AutoQuant, and I think we should get similar results. But yeah, there are some models which have also been, there is QAT applied on top as well. So there is a gamut.
Awesong. Anything else you'd like to share, Abhi?
Hey, Sam, I would like to give a quick shout out to 3 of my colleagues, Kyung-Gyun Lee, Harshita Mangal, and Andrian Bellecci. They helped me put this notebook together for us today. So thanks to them. Also, I would like to say that, please, the audience, please check out AIMET. Let us know how your experience has been, and if there are any problems you encountered or what worked for you, we would be happy to know. And we are always looking for contributors.
Awesome. Thanks so much.
Thank you.